Hi everyone, in today's video we're going to have a look at materials testing and properties. So if you're watching this video in sort of these videos in the sort of order that I would normally teach them, a lot of these things you've seen before, but it's worth having a standalone video as well just to emphasize the importance of certain aspects of it. So what you need to understand basically in terms of the properties of materials are things like what corrosion means. So that might be in terms of like corrosion resistance, conductivity, the difference between destructive and non-destructive tests, what the different tests that you can do on materials are to check those properties, malleability and ductility, hardness, toughness, and tensile strength. So those all essentially are to do with materials properties. Now this bit, if you've already watched through the polymers, the metals and the timbers videos, you've seen this already. Okay, you understand that materials properties make a very big difference. There's a reason why you can't just say it's made out of metal, it's made out of paper, it's made out of plastic, because that's a very generic term. And I always say that's the equivalent of going to Tesco's and saying, "Can I buy some food, please?" Because take metal for example, each metal that exists has very different properties that make it good at some things and very poor at other things. Okay, so it's understanding that whenever you are asked, now typically the key word that you'll find in an exam question is explain why the material is suitable. Whenever you see that word suitable, what it's saying is tell me the properties of that specific material that make it good for this job. So I'll show you a couple of examples at the end of the video, but we'll take for example what the question will be, which is a kitchen sink. So obviously with a kitchen sink it needs to be corrosion resistant and water resistant, because otherwise it's going to rust, or if you're going to put bleach in it to clean it, it's going to disintegrate. So you need to make sure that it is corrosion resistant, otherwise it's not going to be suitable. So with your properties, they are split into two groups. So you've got your mechanical and your physical. So simply put, mechanical are to do with external forces that apply to the material. So I sat on it and it didn't break, or I sat on it and it did break, or I pulled something apart, whatever it may be. And then physical properties do the actual molecular structure of the material, so something passing through it, so how well it conducts electricity or heat or light passes through it, that sort of thing. So that's sort of a general overview of materials properties and why it matters. So these next two slides you have definitely seen before in previous videos. So we'll go through again just so you understand what they're for. So compressive strength is be able to withstand crushing or pushing forces. To put that into context of like a product in a question, it might be asking why stainless steel has been used for the legs of a chair. So it needs good compressive strength, because obviously if something's got poor compressive strength, then pushing down on it, I sit on the chair and the chair breaks, useless chair. Tensile strength is be able to pulled apart. So that might be in things that are moving, for example, say moving parts of like engines and that type of thing, something that's going to be pulled. You mostly have things like in architecture, like in bridges and those sorts of things, where tensile strength, like pulling forces, are acting on something. Bending strength is so it can actually physically bend without like fraying and breaking. Shear strength is sliding past one another in a parallel plane. So what that means is essentially like shears or scissors or that type of thing. Torsional strength means it can withstand twisting. Hardness is the ability to resist abrasive wear. Toughness is impact. Now, hardness and toughness, there's four things that are confused the most. Hardness and toughness are always mixed up. So hardness is abrasive wear and toughness is impact. Those two are always mixed up. Then you got plasticity. So that's the ability to keep to be shaped and then keep that new deformed shape. So you have your stock material, you then form it into a new thing, and then its ability to stay in that new shape. Then the next two are the ones that get mixed up a lot as well, as ductility and malleability. So ductility is it to be able to be stretched without cracking, whereas malleability is to be able to be deformed by compression without cracking. So, but like malleability essentially be like if anyone's ever watched anything on the Discovery Channel where they make like custom bikes or cars, that sort of thing, and they sort of have like compressors with hammers, and they're like forming like gas tanks or seat parts or something like that by hand, and it's malleable because they're compressive, hitting strength around it to change the shape a bit. Excuse me. And then elasticity is being able to be deformed and then return back to its original shape again. So those are the mechanical properties. So then you've got your physical properties, and these are quite simple in that they are essentially what passes through it. So electrical, does it conduct electricity or does it insulate electricity? So does it allow electricity to go through it or does it not? Same with heat, thermal conductor, thermal insulator, or then you've got thermal expansion. So around with the thermal expansion, I've given you the example before. There are certain products or things where you have to remember that certain materials like metal in heat will expand. So a perfect example of that is train tracks. There's a reason why train tracks, if you ever happen to be on a train track, in the cold, they do not always meet up perfectly. Now, the reason for that is it gives it room for it to expand in the heat. Because originally, when they were first trialing out and doing train tracks, they made it all perfectly one solid piece. But then, as it heated up in the summer, the train tracks expanded, but they had nowhere to go. So essentially, they came up and out and broke, and then there were crashes. So you have to take into consideration that some materials will expand in the heat and shrink in the cold. So you need to bear that in mind when you're selecting a material and then manufacturing it. Then you got to do with light. So opaque is light doesn't go through it at all. Translucent is that light will go through it, but it diffuses, so it breaks apart a bit and makes it blurry. So that'd be like frosted glass that you have in your bathrooms. Transparent is that light goes through it, no problem. Density is the mass of a material. Now, you do sometimes get questions in exam papers about calculating the density of a material. We will go through that in the maths content in a later video. You've got fusibility, so the ability for the material to be converted from a solid to a liquid. Magnetism, which is it magnetic or not? A bit self-explanatory. Basically, magnetism will only affect iron or steel, because obviously steel is just iron with carbon to make various different kinds of steel, and then you alloy steel to get stainless steel and so on. Then you got corrosion and degradation resistance. So that's the ability to withstand environmental attack and decay. So that might be that it rusts either outside. It may also be to do with fungal attack and that type of thing. So it's like timber outside, fungal attack, woodworm, rotting, and so on. So those are mechanical and your physical properties. So when it comes to actually testing the materials, they do like to come up in questions about how do you select the right one? Because there are some materials, as you've gone through some of the videos before, that are relatively similar. And there's a few small little differences to like cost or some slightly denser than others and so on. So what you need to be able to do, and it does take quite a scientific approach, is you need to make it a fair fight, basically. You need to make it a fair test. So in order to make it fair and scientific of testing similar or dissimilar materials, is you need to have a sample piece of each material. When you've got a sample piece of each material, they need to be the same shape and size. Then when you've done that, so typically you might test 3 or 4, 5 different, say you're going to make a piece of garden furniture. You may get 3 or 4 different materials that you're considering making it out of. You cut out a piece of each material exactly the same shape and size, and then you would then do your tests. Now your tests have to be scientific. I'll show you what those tests are in the next few slides. Essentially what you can't do is, how will you test it? I just get a piece of material and throw it at the wall, or I just drop it on the floor and see what happens, or I just set it on fire. Because that isn't scientific. You've not actually measured anything, you've not compared anything. It's about how do you make it a proper scientific approach to doing a fair test. If you did higher sciences or engineering, hopefully this is something you've come across before about the idea of making it an actual fair test. So, tensile strength, so that's the ability to withstand stretching or pulling forces. So the workshop test for that will simply be have your material in a vise, have a weight attached to one end of it, and then you keep adding weight and you can measure the amount of distance it travels before it breaks completely to see how strong it is. Next, you've got the toughness test. So this is to do with sudden impact. So you will have your material in the vise or a clamp of some kind, and you need to apply force to it. Now, the best way to make this fair is you would normally have a hammer and have it on a pendulum, lift up a certain amount of height and let go, and it will hit the material. If it bends but doesn't break, it's tough. If it just breaks, it's quite brittle. Next, you've got hardness test. Now, there are 2 kinds of hardness tests you can do in the workshop. I don't know if I mentioned, I'll go back a second. So these tests we're doing now, these are what would be called workshop tests that you do in a workshop in college or a secondary school or that type of thing. These are ones that when it comes to your proper coursework as well, you can test your materials quite easily. I will show you some industrial testing at the end as well. I just want to make sure I said that these are workshop tests. So next you've got hardness testing. So you've got abrasive wear. So that's like basically you would have your material, get like abrasive paper, like glass paper or a file, and put it across. This is basically like measuring like wear and tear, basically. And then you got resistance to indentation. So that is where you get a center punch and a hammer, and hit it with the amount of force and see how much of an indentation in the surface you make as well. So you got malleability and ductility. So this is the most common one that people get mixed up. So remember, ductility is about being able to be stretched without getting damaged, whereas malleability is the ability to deform it under compression, so hitting it with a hammer. So the way you tell it, the test is the same for both. So essentially, have your material in a vise, put a pipe over it, and just pull it down. Now, the reason why it's the same test for both is that what will happen is cracks will appear on either the inside or the outside of the bend. So if cracks appear on the inside of the bend, that means it is not malleable. That means that you cannot deform it under compression without breaking it. Whereas if cracks appear on the outside, it's due to it not being ductile, so it won't be able to be stretched. So that is why there's confusion around it sometimes. Basically, if you try and pull it down and it cracks on the outside, it isn't very easy to stretch without getting damaged. Okay. Next, you got conductivity testing. So we'll take electrical first. So you'll just have your multimeter, have probes on both sides, send an electrical current through it, and see how much of a current appears on it. Then the other one, you've got thermal conductivity. So you'd have your piece of material, apply heat to one side, have a thermometer on the other side, and time how long it takes for heat to actually travel all the way up to the other side of the material. Corrosion testing. So this basically determines how fast something will corrode when exposed to environmental effects like the rain or the sun, or it could also be to do with chemicals like bleach or that sort of thing, depending on what you're trying to do. So essentially, the material can just be left in the environment for a predetermined amount of time. So it could be that you take all your samples and you leave them in a controlled environment outside for a day, 2 days, or you leave it in a tub of bleach or whatever it is, and you just over time, as long as they're all in for the same amount of time, you just then check the results and see what the damage is to it. So those are the workshop tests that you can do. So what we're going to have a look at now are the industrial tests. So these are ones that you're not going to have access to. These are done on a much more industrial scale, but they are very, very useful, and they do come up in exams as well. So then first you've got tensile strength. So here we'd use a tensometer machine. So hopefully you can see my mouse that's appearing on my screen there. So work clamped into each end. So basically you've got 2 clamps here, 1 and 2. Work is clamped in place. This part here, the stationary base, this doesn't move. Okay, the top part is on a worm drive. So what that means is basically it'll start in a neutral position and it will move up the worm drive at a constant rate. What that will let you do is that you'll have this all set up on a monitor, so you can actually tell how one, what speed you're going at, and two, the amount of force that's being pulled apart. So it'll let you check elastic limit, the yield point, maximum load, and then the final breaking point. So you can actually, each material, as I say, doing 3 or 4 different tests, let you plot out which ones lasted the longest, which ones had the strongest point, and so on. Then you got the toughness test. So this is called the ISOD impact test. So material is clamped into the middle, so it's right down there, so it's clamped vertically in the machine. The pendulum is brought up. Now I said before about being able to do the test and it was with a hammer and on a pendulum. Same sort of thing, but the difference being here is that you could bring the pendulum up and it would actually be locked in place. So if you're doing a workshop test in college, you set up a pendulum and you just lift up the hammer by hand and then release it by hand, whereas this would be the case if you have the pendulum, you lift it up, lock it in place. There's an energy meter at the top, and essentially you'll then release it from a set position, and then you can calculate the amount of force that it absorbed based on the height and the speed that it was going at. And then obviously to make sure it's a fair test, you'd set the height the same for each one of those materials. Then you got hardness testing. Now there are actually 3 different kinds of hardness testing depending on the kind of material that you're doing it on. So the first one is the Rockwell test. So this, to begin with, you have your preload applied to the material using a diamond indent to break the surface. So that is this one here. So you'll just break the surface a little bit with a diamond coated tip because it will be hard enough to break through the material. Then when you've done that, additional load is then applied to determine like over a certain amount of time. So once you've broken the surface, that's your starting line there. That's why that's called your zero reference line. So you can start there, and that will be essentially where you've started from. Okay, so you're not starting from the absolute surface, you're starting from just, essentially you're breaking the surface and you're trying to test the inside hardness of the material. So you're going to break it through a little bit and then you're going to press down for a certain amount of time and then you'll come back out again. And what you're going to look for is the difference between the first line you did and then the last line that you did. And that will determine how hard that material is. Okay. Next, you've got the Brinell test. I hope I'm pronouncing that right. I've only ever heard it or read it in books as opposed to actually heard anyone say it out loud. So it works in a similar sort of way. So basically, you'd have a standard size steel or carbide ball, and this is forced into the material. Again, none of this is done by hand. This will be done by a machine. So the force is always the same. And what you will look for here, rather than how again, you're not going to have an initial break of the surface. What you're going to have is it's going to be a straight surface, press the ball in, and you're going to measure how big the diameter of the hole that was produced is. The smaller the indent, the harder the material because less of it's been pushed through. And the final one is the Vickers pyramid test. So this is for very, very dense materials that would typically be very difficult to break into. So it works very similar to the Brinell test. So the reason why they use a diamond pyramid is because diamond will not distort under pressure because this is typically used for very, very hard materials that would be quite hard to determine on a normal test. You would press down and then similar to the Brinell test we just did with the ball is you just measure the diameter of the indent to see how tough it is. The smaller the indent, again, the harder the material is. Now you've got non-destructive tests. So you've got ultrasonic testing. So this will usually use on larger items that you may not be able to physically get to, whether maybe some like internal defects, that way, like oil pipelines, submarines, oil rigs, that type of thing. So essentially sound waves are just pulsed into the material and those sound waves will go through that material and if nothing's there, the sound waves bounce back, it comes up on a monitor and the waves are the same going forwards as they are going backwards and that's fine. If there's any defects, if you see on here, so basically there's no defects here, so sound wave goes in, bounces on the end, comes back up again. And on the monitor you'll get this sort of reading. So if there are any cracks or anything like that, the sound wave will bounce in and come back up again, but it won't be as long as it should be. So you'll have your measurement of what a perfect sound wave would be, but if it comes back shorter, that means, oh, there must be an error there. It's used a lot, as I said, like offshore industries, aerospace, that sort of thing. And non-destructive, the whole reason why the term non-destructive is you're not, like with these similar tests here, where you're breaking into the surface of the material, you're not doing that with these non-destructive tests. Then you've got X-ray testing. Works in a pretty similar way to ultrasonic testing, except this way it's X-ray beams that are passing through the material, and that will bring up on the monitor any defects that you see. So basically passes through, and then anytime there are defects, darker areas will show up where there are defects on there. So looking at this content, realistically, you're going to join it with 2 or more different topics together. So it may be that part 1 of a question is showing you a picture of a product and it asks you to name a suitable material. Next part might be that it says, okay, can you please explain why that is suitable? And for that, you have to then talk about the properties of the material. And then how would you test it? So that could be a 2, 3, 4 part question, like an A, B, C, D, building up. So you have to make sure you understand the testing, but also the materials properties and maybe the manufacturing processes as well. So this is why a few topics are linked together. So we're going to go through a few questions. So first one, explain how a comparative workshop test for hardness will be carried out in order to select a suitable wood to manufacture a children's toy. Okay, so 8 marks, so that counts as a long marked question. So because it has not explained, it's not asked you to discuss anything, only explain, then you do not need a conclusion. If it asks you to discuss something, that's when you need to have an introduction, your main argument, and then a conclusion. Now it's just asking you to it's only asking you to explain it. Okay, so if you look at it, 8 marks. So really, you're looking for 4 points, and then you're looking to back up each one of those 4 points with an explanation, and that's how you get your 8 marks. So basically, what you'll be looking for is 4 steps to doing your workshop tests. Okay, so a good habit really is to make sure you are highlighting the key tests, the key words, sorry, for the question. So if this one, if you look at it, I've got comparative, hardness, and wood. So you're looking to set up a few tests where you're going to compare a few different types of wood. Okay, so you might, for example, MDF, plywood, and then some natural timbers. Maybe you can have some pine, maybe some oak. So imagine you've got like 3 or 4 different pieces of material because you're going to compare them, and you're going to test them all for hardness. So how are you going to make sure you can do that and do it accurately? Okay, so just like I said there, make sure you understand the wording. It wants you to explain how to test a range of different woods in terms of their hardness. So we're talking about hardness here. So you want to remember, what was that test for hardness? So you got 8 minutes. Pause the video, give yourself 8 minutes, use the textbook, try and answer the question. Okay, so 8 mark. So what you could do, so you'd have your samples of each material, each timber wood, and you'd have the same size and thickness because that's how you would make sure it's fair. So, for example, pine, beech, ash, you might have man-made boards, like I said, plywood, MDF, anything like that. You would then have the center of each material marked out because if you're going to do it, you need to make sure that you're doing it the same for each piece of material, so it's accurate. So you'd have the same type of thickness, the same size material, and you'd hit it in the same place because all of that is how you make sure it's going to be a fair test. So the hardness test, remember there was 2. So we're going to do the dot punch test. So that's where you have your center punch or your dot punch, and that's placed in the center of the material. It's then hit with force. Now the force must be the same for each material, so that will be with a hammer. So what you would want to do is set up a jig so you've got a hammer on a pendulum. So you're just dropping it, because if you're just trying to hit it with your hand, not with your hand, but you're holding the hammer, you're never going to get it accurate the same each time. And then you'd see how much of an indent is left in the material. So that is, it's how much it will indent. The next one is the abrasive wear, which is the scratch test. So that is where you would get either glass paper or a file and rub it across the surface and see how it damages it as well. So typically then, the smaller the indent, the harder the material, and then you would decide that the hardest material would be the most suitable for children's toy. Now the reason why hardness matters children's toys is because children are rough and they like chuck toys around, they drop them, they bang them into things. So that's why you would do a hardness test to make sure that it is going to be a suitable material. You don't want a material that is going to like disintegrate once a kid starts banging around with it. Okay, so if you look on the marking criteria down the left hand side, so to get 6 to 8 marks, so it's full explanation of testing process, including this test setup. So that's talking about getting your materials with the same thicknesses, marking it all out. Explanation of how the test is carried out, so explaining the actual part of it, so that's 2 marks. And then control measures, so how do you make sure it's all going to be done accurately, and then what your findings will mean. Okay, so there's 4 points in there. So obviously, like I said, 8 marks, 4 points, and then an explanation to go with it. Next question. So describe a simple workshop test which could be carried out on a range of materials in order to investigate 2 of the mechanical properties from the list below. So 12 marks. Okay, so 12 marks is definitely a long mark question. It's asking you to talk about 2. Okay, so there's 6 marks of 12 marks. Okay, talking about 2 things, so automatically divide it by 2. Okay, so if you're making hardness, tensile strength, toughness, or ductility and malleability, pick any of those 2, it doesn't matter. Okay, then half the marks, so you need to get 6 marks to talk about hardness, 6 marks to talk about tensile strength, whichever one you're picking. Now, with those 6 marks, basically, you then need to just get 3 points for each one. So that gives you 3 marks, and then explain yourself in more detail. Remember, in these big ones, because it's telling you how many, divide it by that number, and then you always want to half it because you get a mark for bringing up the point, then a mark for explaining it as well. So you've got 12 marks, 12 minutes. Can you pause the video, give yourself 12 minutes, use the textbook, have a go answering. Okay, so destructive testing, 2 from hardness. So you can have hardness, tensile strength, toughness, ductility, malleability. So the test for hardness. So softer metals are more easily filed. So that's where you would do like your abrasive wear, where you'd have like a file or glass paper. So like your indent, your dot punch. You have to make sure that you're using the same amount of force for each one. Tensile strength will be where you have your material clamped in a vise, and then you would measure how much force it takes to bend it. So you'd apply a scale and weight and keep adding weight until it starts to break, or starts to bend rather, sorry. Toughness, so you clamp your material in the vise and you would strike it with a hammer. So then obviously we talked about you have to set that up with a jig to make sure it's on a pendulum, so you're being fair and doing an equal amount of force. Now on these, you notice it's doing things like the Hounsville test. These are more industrial tests than workshop tests. What you can, the way we're explaining it now, will get you the marks, not a problem. So ductility. So clamp your material in the vise and try to bend it at an angle and look at where the cracks appear. So what it says as well. So reward label sketches as appropriate. So the best way to get marks, in my opinion, okay, so you've got to get 6 marks for each one. If you can draw a diagram to explain it and annotate it and then do a little summary at the end of it, that's going to be the best way to get the marks, okay? So next one, we have seen this question before. The photograph below shows a kitchen sink that has been manufactured from stainless steel. Give 2 physical and 2 mechanical properties of the metal used. In each case, explain why that property is suitable for this product. So 8 marks, 8 minutes. Pause the video, give yourself 8 minutes. Okay, so we get 1 mark for relevant material property and 1 mark for saying why that matters. So mechanical properties, you could add hardness, toughness, and malleability, and explain what it means. And then your physical properties, resistant to corrosion or chemical resistance. And as long as you can come up with the property and then say why it matters. So for example, if we take like resistance to corrosion, it means it's not going to rust, so you can actually turn the taps on your sink. If you take like hardness, it means if you were to like chuck your cutlery into the sink, it's not going to scratch and ruin the sink. So that is the end of materials testing revision. Please, if you want to go over it again, have a look at the first year video as well, and on the SharePoint there is the bank of questions. If you've got any questions you want to ask, please do email me.